Okay, hello everyone and welcome to this lecture. In the continuation of the last lecture, today we will prove some more results on largest eigenvalue. In the specific, today first we will compare the kind of comparison of eigenvalue of the largest eigenvalue of subgraph with the largest eigenvalue of the parent graph. And then we will see what could be the relation between largest eigenvalue and the maximum degree or minimum degree or average degree. Okay, so let us first start with the kind of relation between the largest eigenvalue of a subgraph to the largest eigenvalue of its parent graph. It's not exactly a relation, but basically some kind of inequality, whether the eigenvalue will be less or equal to or greater or equal to. Okay, so let me first write this. Okay, so theorem. Okay, very good. So let H be a subgraph of G. Okay, then very simple to state, then the largest eigenvalue of H, the largest eigenvalue of adjacency matrix of H is what? Always less or equal to the largest eigenvalue of adjacency matrix of G. First thing is this. Okay, second thing, if G is connected, second thing, if G is connected, if G is connected, then these two eigenvalues are equal if and only if they both are same. If both are, means the graph and H are both are, then lambda 1 AH is equal to lambda 1 AG. I hope it is not cutting. Okay, AG if and only if, and only if both the graphs are same, basically H equal to G. Both the graphs are same vertices, same edges. Okay, let us try to prove it. I hope by now we have a very good warm up on proof technique what we will follow in case of when we are using eigenvalue, especially the largest eigenvalue on eigenvector. Okay, so let's suppose I denote the adjacency matrix A by some general element Aij, and by Ag some Bij. Okay, now remember H is my subgraph. See, I am not telling about the induced subgraph. It can be any subgraph. Okay, so basically, so if you see here, there are suppose edges here, right, in graph, right? Suppose this is my graph, and out of those many edges I am picking some edges, some vertices, right? So, and I told you that this might not be induced subgraph. Okay, so there can be some AIs, the corresponding BI will be 1, but AI may not be 1. Okay, so basically we are not choosing all the edges which are falling on the vertices of H, all the edges which were present in G. So this is the that was the definition of induced subgraph, right? So here the subgraph can be anything. Okay, so there may be some AIJs whose value is 0, but the corresponding BIJ is not 0. Okay, so now largest eigenvalue of AH. Okay, so suppose so largest eigenvalue of AH is this, of AH is, now let's suppose X is some eigenvector to it. Okay, so and so basically AH times X. Okay, so I will write down, I mean, left to right, no issue. Okay, very good. And this implies that this, right, we have seen in multiple X transpose AH times X transpose is indeed equal to lambda 1 of AH. Very good, right? And this sorry, and this quantity, in fact, if you see, this quantity is nothing but this summation over aij, all aij and xi xj, summation over all aij, right? Summation I can write ij equal to 1 to n and so on, right? All. Okay, good. And this is equal to lambda 1 ah. Very, very simple. Okay. Now what? Let's suppose y is some vector, okay, which is kind of extension of y is, let me write this, some vector which is an extension of x. Remember, x size will be what? The number of vertices in H, right? G is what? So suppose that number is m and G has n vertices. Okay, so x dimension x, how many entries in x will be? There will be m entries, right? And how many entries in and y is some vector which is extension of x such that the number of entries in y is first of all n, and okay, such that the number of entries in y is n. Let me write in a bracket that n is the number of vertices in G. Okay, and basically the extra, so it's you assume that there is the same x, but there are some extra entries. The extra entries are 0. The extra entries are 0. Basically you are copying, so somewhere by law, without loss of generality, you can assume that y is this vector, okay, somewhere here this is x and there are some zeros, just to make it a vector having n entries. Okay, so rest of the entries. Now if you see here, so what will be this quantity? If I do this y transpose a g y, this will be nothing but summation over again ij. Now ij are varying over 1 to n, right? Then bij, because ag I have the general entry are denominated by bij, and then what? Yj. Very, very simple. Now what is the relation between this quantity and this quantity? If you see that, I told you there might be some bij which are 1 and the corresponding ai's are 0, because we may not, because the graph may not be induced subgraph, right? So basically, and yi and yj are, nothing but ij, and sometimes we are adding with zeros. Okay, so wherever I and j are 1, the corresponding yi and yj are definitely 1, and some of y entries in we are padded with zeros. Okay, so this quantity is nothing but very, very simple now to follow, is this, that summation over aij, then xi xj is always less or equal to this quantity, right? Bij vi vj, sorry, yi yj, and this quantity we already know, right? This is lambda 1 of h. Very, very good. But and this quantity is equal to what? This y transpose agy, and we have seen that this quantity is always, for any vector, this is always, basically lambda 1 of g will be lambda 1 of ag, I would say, always greater or equal to this quantity. So what? And I think we are done. So this implies that lambda 1 of, I think this is ah, I am making a lot of mistake here, of ah is always less or equal to lambda 1 of ag. So very, very simple to follow, right? Okay, so very, very simple result. Okay, now the next thing is, so this is about 1, and g is, if g is connected, then lambda 1 equal to lambda if and only if c. I think the second thing, if suppose, okay, let us suppose these two eigenvalues are same. If these two eigenvalues are same, then if you see that from this inequality, so let me write it as what, actually I have written 1 and 2 here. Anyway, so it is very easy to follow. Let me write this mark here. So if these two quantities are same, right, that means everywhere there is a equality. Basically this means that summation over aij xi and xj ij is equal to, indeed, again let me write here ij, okay, I comma j. Here ij for is from 1 to m and here 1 to n, right? Okay, so nothing to bothering here. So yeah, yi yj, very good. What next? And this is indeed equal to y transpose ag y and lambda 1 ag. Okay, by the way, if I have, I'm sure I must have told you that the vector x I am taking is by default a non-negative vector, because I can always take a non-negative vector corresponding to the largest eigenvalue. Okay, if I'm not set, I mean I can always take this, right? Now, so that means y will also be, so let me here write this x was nothing but non-negative vector, non-negative vector. We can always choose a non-negative vector corresponding to the largest eigenvalue. Very, very simple one. Okay. Now, if you see that, yeah, so since x I am choosing non-negative, y will also be non-negative. Y is also non-negative. Okay, and since g is connected, in the second condition, if you see that since g is connected, that means there is no zero entry. Since g is connected, there is no zero, there is no zero entry in y. And before that, actually this because this is equality everywhere, I'm very sorry, I'm making silly mistakes here. This has to be equality, right? This has to be equality, and this will imply that y is an eigenvector of lambda 1. Y is an eigenvector of ag. Extremely sorry for the mistake I did. It was not mistake, but it was negligence, I would say, of IAG. And now since, and y is non-negative vector, since z is connected, all the entries in y must be positive. Okay, since there is no zero entry in y, okay, everything non-zero, in fact everything is positive. Okay, very good. Now what can you say about, again let me write this equality again. This equality is what? So ij aij xi xj equals to I comma j bij and y. Remember, all ai are non-negative, all bij are non-negative, x is non-negative and y is also negative. More than that, y is always positive. Okay, there is no zero inside y. So if you see that, because y is coming from x and there are some padding to x to give y, right? So all the corresponding entries in x will always be positive, right? So so what does this imply? What will this imply? Okay, what will this imply? Now in order to this equality to hold, right, what do you think, what will be? Because if you see that, firstly all the entries are what? 0 or 1, right? 0 or 1, similarly 0 or 1. Okay, whenever this 0 will be there, this whole term will not exist, similarly here, right? and all these are positive. So first thing is, in order these to be equal, the number of terms on the both hand sides should be same. Number of terms with the both hand sides should be same, because terms are positive. The value is always positive. So in order to equality, the first thing is, and these terms are what? If you see that these are 0, 1, 0, 1, and xi and yi are the same order. So they has to be, the number of terms should be same. This will imply that all aij equal to bij. That means whatever the edges were earlier, the same edges are here, right? The size is also same. This implies further that G is indeed equal to H. Okay. The opposite direction is very simple. If G is equal to H, then of course the eigenvalue, because it's the same graph, so largest eigenvalue will be the same. Okay. So very simple proof. Okay. And remember, don't confuse that this H is actually induced. No, this can be any subgraph. Okay. We will see in the next lecture, maybe we will prove one very beautiful theorem, using which we can actually directly say just by looking at the subgraph. If that subgraph is induced subgraph, what will be the eigenvalues with respect to the original subgraph. Okay. But in general this is not true. Here this result is true even for the graphs which are not induced. Okay. So very good. I hope this is clear. Now let us move to another interesting fact, that a fact which relate the largest eigenvalue with the average degree and maximum degree of graph. Okay. So let us again start. Okay. So let me write the theorem. Okay. Let G be a graph. Okay. With lambda 1g, I will tell you the by mean of this is lambda 1g is the largest eigenvalue of adjacency matrix of G. Okay. Let G be a graph. Then the largest eigenvalue of G is always less than or equal to the maximum degree that I will define by this. Okay. I will denote it by this, but it is greater than the average degree. So let me denote it by this. Okay. So where is the largest degree, comma, is the average degree, the average degree of G. Okay. So let us prove this fact. Very simple one. Okay. Proof. Okay. Let us first prove this fact, average degree, right? We know that lambda 1 of G is nothing but, I will just write lambda 1 now, is always what we say is greater or equal to X transpose adjacency matrix of this, right? X you are taking in unit vector everywhere. Whenever I write this, you assume that X is unit vector. Okay. But suppose I take X is equal to all one vector, all one vector. Okay. In fact, I can actually divide it by this, because X, the X I will choose is actually not unit vector. So if in case X is not unit vector, you assume this, right? We have to follow this. So suppose X is all one vector, okay, of n. There are n entries, right? So I can actually write this, lambda 1 is always greater or equal to all one this vector times AG times all one divided by, again write this. But what is this quantity? This quantity is what? Basically it's adding all the entries of A. This is adding all the entries of, and how many entries are there? There are many ones, right? How many ones? Which is equal to twice the number of edges, because an edge is counted twice. Okay. So this is equal to twice the number of edges. M is edges, is the number of edges, divided by what will be this quantity? This is n, the number of vertices, the number of vertices. Okay, very good. So yeah, now now it is very clear. What is 2m? 2m is nothing but sum of degrees. sum of degrees, I equal to 1 to n. So di is degree of vertex I divided by n. Okay, so now what? Yeah, and this is average degree. Oh great, this is nothing but average degree, right? So lambda 1 is always greater than the average degree of J. You're done. Proof is done. Okay, so first part is done. In fact, it is, yeah, okay, so one side is done. Now next is we have to prove that lambda 1 is smaller than, is smaller or equal to the largest degree. Okay, so how to proceed with this? Again, so let us take some eigenvector of lambda 1. So suppose, and that I will take maybe unit vector, yeah, I mean, or I don't know, I mean, we can always take, but here may not be used, right? Yeah, okay, so suppose x is eigenvector corresponding to lambda 1. Okay, and what? And if we see that, suppose the ith entry of x is the entry with largest modulus. Okay, so suppose xi is the entry in x with the largest absolute value. Okay, so that means I can write this as, and lambda 1 is always positive, right? Anyway, let us see this, what will this. So that means if I write the ith entry of this vector, so what it will be? So lambda 1 xi, okay, and in fact I can write this as, right? So, and this will be equal to, because lambda 1 is always, so this I can write it, in fact this also, right? I hope this is clear to you. I hope the mod of this quantity is nothing but mod of these two. Okay, very good. And what? The next thing is, this quantity can be written as what? This quantity can be written as, yeah, this is nothing but, first let me write this and then I will take mod of this. So summation over all, and suppose A is my, this matrix, the general matrix is this, right? AI and what I should do, I mean J, if I vary, yeah, Aij, okay, I equal to J equal to 1 to n, in fact. Okay, so let me, because I am varying over J, right? So this is nothing but matrix product. Come on, J equal to 1 to n Aij, and then all the neighbors of the, basically if I am multiplying with this vector, right? So this is xj. Okay, I hope this is clear. What this is nothing but actually matrix product from here. Okay, so ij and you are taking xj. Okay, very good, and mod of this. Okay, now this quantity, because aij's are, this quantity I can always write, if you break this in terms. So I am taking all aij's outside, and this, basically summation over, I can write j equal to n. Okay, aij and xj, so I can write this, right? Aij, mod aij, and then mod xj, because I am taking the sums, right? Okay, so I hope this is clear. This quantity, you can write it as this. And now what? This quantity is further, because xi has the largest modulus, right? So I can write this as mod xi times this sum, right? I equal to j to n. And by the way, what is this? Aij, there is no need of putting mod over here, because these are either 0 or 1, so not negative, so no issue here. Now, so yes, this is correct. Now what next? If you see that this is nothing but this, if you see that this is a degree of vertex I, this is nothing but degree of vertex I, okay, which is always less or equal to the maximum degree. okay, which is always less or equal to, so that means that I can further write at this, right, mod xi times this maximum degree. Now we can relate these two quantities, this one and this one. This implies that mod lambda, this is okay, I am making one mistake here. This is lambda 1. I am extremely sorry. Again. Okay, so this is lambda 1 and okay, so yeah, very good. So lambda 1 and then lambda 1 is always positive, by the way. So you can actually now derive here that lambda 1, or see this is simply I can write anyway. No, there is no issue in that, but let me write for completeness is always less or equal to maximum degree, and you can cancel these, okay, because this is the positive number, non-zero, okay, and you can cancel that. This implies that lambda 1 is, because lambda 1 modulus, because it's always positive, right, it's always less or equal to maximum degree. Okay, in fact we can say something more. We can give a bound on largest eigenvalue in terms of square root of delta g. So let me first write it. What is this? So lambda 1 is always greater or equal to square root of delta g. Why this is true? Why this is true? If you see the graph and if you pick a vertex with having degree delta g, so that means it will look like this. So basically there is a vertex here and delta g number of edges are incident on it. Okay, so this graph is what? This is a complete graph, complete bipartite graph k1 delta g, where there is a one vertex in the center and rest of the vertices are connected to each. So basically these vertices make another partition and one partition is just by that vertex, okay, the center vertex, let us call it V. Now we already know the largest eigenvalue of a complete bipartite graph, right? So what is that? The eigenvalue here is nothing but square root of delta g. This we have already seen maybe 2-3 lectures before. And the largest eigenvalue, this is a subgraph, okay, so largest eigenvalue of subgraph is always less or equal to the largest eigenvalue of our original graph. Okay, so with this, in fact, so this is also true, delta g. So we have given both the bounds in terms of delta g, the largest degree of graph. Okay, with this I am stopping this lecture. I hope you got these basic facts, okay, and see you in the next lecture. Okay, thank you very much.